now.
All right. Hi, everyone. So today our own Sam will be giving a talk on the variance analysis of unbiased MCMC estimators. Now let Sam take it from here.
Great. Thanks, everyone. So so today I'm just going to present some work in progress to do with some recent MCMC estimators that have sort of been a bit popular over the past few years. One thing I'm particularly interested in is getting people's ideas for other stuff I could do within this framework. You'll see that I have proved some things, but I think probably there's more interesting stuff to do or extensions to consider. And so feedback to that effect would be particularly useful. Okay, so at the start, it's just setting the scene. I won't even define what MCMC is, but I will go straight into the estimator, okay, because for our purposes, that's what's happening, right? So the broad strokes of computing an integral via MCMC, at least at some level of granularity, is as follows, right? We initialize our chain at some point x0. We run the chain for b steps of burn-in, during which we hope that the chain reaches stationarity or something close to it. And then after that, we run the chain for another capital T steps, and we collect samples, and then we use those samples to estimate the integral. We take the sort of empirical measure of those T steps as our approximation of the target. And okay, so this is, something you can do with finite b and finite t, and that is an estimator of your integral in some sense. And so you can ask reasonable questions about whether this estimator has a bias associated to it and what the variance associated to it is, right? And so a great deal of work goes towards both of these questions. And today the focus is mostly on the bias aspect and then subsequently on some variance things. But a key thing to observe early on is that if I initialize at a point or, a point from some approximation to the distribution even, most of the time there will be some bias in this estimator for some functions. And you sort of think it's the typical case that you will have some bias. And so something which people have been interested in is to find ways of mitigating this bias, either to get rid of it completely or to reduce it to the stage that that you don't have to worry about it, right? At the end of the day, our estimators, they're randomized most of the time, and so you're going to have some stochastic error involved. And so the point of bias reduction from my point of view is sometimes to remove it completely, but mostly to reduce it to the stage that you don't have to worry about it, to make it a sort of lower order effect. This is sort of true in statistical estimation in general. Okay, so one methodology which has sort of been proposed in the last 5 to 10 years, depending on how you count it, is this notion of unbiased MCMC, where I mostly associate it to this paper of Jacob, O'Leary, and Achede, which is published in JRSSB a couple of years ago. But there's sort of symptoms of the idea in earlier work of Peter Glynn and his PhD student Chang Henry. And so the idea is essentially, so we want to compute the integral of some function f under a thing pi, and we have a Markov chain xt, which is converging in distribution 2 pi. And so we know that this first line is true by the ergodic theorem, okay? And indeed, you can consider a sort of averaged version of this, where instead of just looking at the function at the final time t, you average over L steps, okay? Now, by pulling the factor of 1 over L out the front and writing this sum as a difference of two things, I'm going to start time at -L for reasons that will be more convenient later, but conceptually nothing strange is happening there at least. Okay, so you have this equality here. And then to go from the third to the fourth line, I say I'm going to introduce some process yt, which is also a Markov chain, which has equality in distribution between xt and yt minus L. Okay, so it's sort of, they are at some lag to one another, the same law. Okay, and then by shuffling the terms around here, you get this final expression where, pi of f can be estimated by, you take the average of f along the sort of negative time indices here on the first chain, and then you have this correction term over here on the right-hand side, okay? And so this suggests a Markov chain estimator that you can consider. Again, I've not said anything about why it would be good or anything yet. the YT does not have to be independent of the XT, crucially, and indeed we'll see that making it depend on the XT will make things interesting. So in the work of Jacob et al., the standard thing to do is to then send t to infinity and construct the chain such that this this sum over here is finite. What I'll argue is that from the analysis point of view, it's instructive to show what the estimator looks like at a finite t, and then send t to infinity later on. Okay, so you sort of prove a more general result, and then you deduce the thing you care about after that. Okay, and I'll sort of, describe this algorithm in a couple more ways in the coming slides. Okay, right, so the algorithm is as follows. So I'm going to have 3 algorithmic parameters here. One will be B, the sort of burn-in time, L, which will be the lag between the 2 chains, and then T, which will be the terminal time at which I stop running the chains. Okay, so at time -L minus B, I initialize my first chain at X, and I run it for L steps up until -B. Then at that time, I give birth to a second chain, also initialized at X. And then from there, I run a coupling of the 2 Markov kernels forwards in time for another B plus T steps. So up until time 0 and then forwards from there. And in practice, we're going to see that it will be useful to run these coupled kernels such that the chains get closer to one another, right? I think from a theoretical point of view, this is the usual thing you do with couplings. But in this setting, it's sort of explicitly what we want to do, okay? And so to construct our estimator, what we will do, we'll be using these chains, we will collect the samples from the first chain from time -L to -1. And then using the difference between the 2 chains for time t greater than 0, we'll sort of look at the difference between them, and that will form our bias correction. And so there's a sort of illustration here. This is the bit paper I promised you, Andy. So here, so for the first L steps, the X chain is evolving, by itself. There's no second chain. At time -B, we give birth to the second chain, and then we evolve them in parallel. So that's what I mean by this this vertical line here, is that the transition kernel of X and Y are sort of dependent in some interesting way. And so in terms of constructing the estimator, if we want to estimate the integral of f under pi, we use the sort of standard MCMC type estimator based on these samples from the X chain from time -L to -1. And then using these chains here, we have that sum of f of xt minus f of yt for t greater than 0. That will sort of account for the non-stationarity and so on. Okay, so, and then this is just me writing the estimator again. I've sort of suppressed the dependence on B, which will become important later on. Okay, and so as I said before, throughout, I'm going to analyze this with a finite t, because that's a perfectly valid thing to do. Again, it's like you're just constructing an estimator. In practice, it's of interest to make these chains xt and yt coalesce exactly at some random but finite t. And then that means you can effectively take t to be infinite, because most of this sum here will be 0. Okay. But I will actually not talk about the coalescence too much, because from the stuff I'm talking about, it's not so important. Okay, so a good question is why you would use this estimator. And so you'll see this spelt out to varying degrees in varying places. But the way I perceive it is that you essentially want it to be something that functions more or less like your standard MCMC estimator, but it also happens to be unbiased. So you're not expecting magic to happen. You're not doing something dramatically better. You are doing sort of ideally what you would do with MCMC, but without this extra thing to worry about, okay? And so some basic desiderata you would have for a method of this form is that you want the cost of running this unbiased estimator to be bounded above by the cost of, or the time it takes for the Markov chain to reach equilibrium, basically, times a small constant, let's say. I think that's sort of ideal. And you also want that the variance of the estimator you get is comparable to the variance you would get of this biased MCMC estimator run for that amount of time. Okay, and so here you really want to think of A and B as maybe being 2, 3, or 4, something like reasonably small. And if these desiderata hold, then you can run these unbiased estimators in parallel on different machines. And you would expect that in the same amount of time it would take you to get one Markov chain to reach equilibrium, more or less. You can get all of these chains to mix enough, and you reduce your variance by a factor of p, and then you sort of pay this small price for the inefficiency introduced by doing something fancy somehow. So from my point of view, this is what the methodology might promise to achieve. Okay, I'm not expecting much more than this, just that you get something about as good as MCMC, but the bias is removed, and hence with this parallelism, you can do new things for variance reduction. From my point of view, without the parallelism, it's a less efficient method, which is at least unbiased. The appeal is potentially there, but it's much clearer for me in the case where you have parallelism available to you. Okay. I should say if people have questions, just jump in. Okay, so let's move on from here. So how are we going to analyze such a process? So we don't strictly care about convergence to equilibrium because we are just caring about the estimator, right? That's the name of the game today. And indeed, convergence to equilibrium is slightly fiddly here because we have a fundamentally non-stationary process where you start it out of equilibrium and then you run it. And just as things are looking good and the chain is pretty close to the invariant measure, you actually kill it, right? So you don't get to see the equilibrium behavior to some extent. And so one perspective on that is that if you're going to use this sort of a method, you need Markov chain tools that are well adapted to systems that are out of equilibrium and perhaps non-stationary. And so the tool I'll use is what I'll call contractivity, and I'll spell this out more going forward. Another sort of vague point to make is because this methodology is based on couplings, it is natural to use an analysis which reflects the couplings somehow, that sort of plays nicely with the properties of the couplings that you implement, say. Okay, so the standing assumption here is a contractivity or curvature assumption on the Markov kernel that you're using. And so the premise is the following. So you have your Markov chain, it's evolving on some state space, and usually without any extra effort, you can come up with some metric on the space. And so what we're going to assume is that there is a particular metric on this space, which is maybe a bit of a weird one, right? It's maybe not the metric you would work with naturally, a sort of discrete one or a Euclidean one. And so we're going to assume that for a fixed kappa in 0, 1, which I'll call the contractivity coefficient, it's always possible to couple your Markov kernels such that if you have one kernel starting at X and one kernel starting at Y, that after one step, on average, the chains get closer together, okay? And so I'll really insist, like, you don't have to get them closer together deterministically, it just has to happen on average, okay? And so this has a few different names. So you'll hear it referred to as coarse Ricci curvature, which is sort of related to some differential geometric notions. More recently, it's common to hear it also referred to as Olivier-Ricci curvature because of work by Jan Olivier on this topic. And occasionally you'll also hear it referred to as sort of transport contractivity or Wasserstein contractivity. Although I try not to use Wasserstein because he didn't actually do a great deal on transport stuff, as it turns out. Okay, so this is the real key assumption, and I'll sort of examine how reasonable it is going forward, but I hope the basic definition is clear. So it sort of says, on average, you can couple kernels to move points closer together in some metric D. Okay, so you can say that's a very nice assumption, but is it ever true? And so what I'm going to do here is catalog some familiar senses in which it can be true, okay? So if D is the trivial metric, so it's only 0 when the points are the same and it's 1 otherwise, then actually this contractivity condition is what's equivalent to a what's called a Dublin condition or a uniform manorization condition. Okay, and this is sort of a very strong one. It typically you're requiring complex state spaces or very dull chains in a lot of ways, although that's not completely fair. And if you're interested in this, there's a nice paper by Delmoral, Ledoux, and Miclot, where they study the implications of this condition for things like sequential Monte Carlo, where it's particularly relevant there because you have time inhomogeneous processes typically, but you want to have good control on the behavior of the process. Now, if on the other hand, you have D just being a Euclidean metric, then the standard example of when this would hold would be when you have a diffusion, say an overdamped Langevin diffusion in a strongly convex potential. You can sort of feed the diffusions the same Brownian motion, and they will deterministically contract, actually. And so this is related to what people would call Bakry-Amory theory, and has serious connections to convexity. Another example would be if you were simulating a piecewise deterministic Markov process, where the dynamics that you're following, the ODE, is just contracting towards a point, say, and then you refresh in some way at, Poisson times, say. But the first case is by far the one you'll see most often in the literature. If you take D to be a Hamming distance, so you imagine you have a sort of a vector of discrete things and you just count how many coordinates the vectors differ in, then the contractivity condition is equivalent to what's called a de Bruijn condition, which is useful for studying Gibbs samplers and stuff like this. And actually de Bruijn's paper is where he sort of calls these things Wasserstein distances for the first time. Okay, so these first three I would say are typically pretty strong conditions, which in many practical applications you wouldn't expect to hold per se. There are some variations where you can take D to be the sort of trivial metric in a weighted sense, where basically if X and Y are distinct points, you say that the distance between them is f of X plus f of Y for some positive F. So basically, you punish the points for being far away from the center of the space, typically, but you don't care if they're far away from one another. Okay, and so this is related to techniques to do with Lyapunov functions and minorization conditions. And there's a really lovely result of Martin Heyer and Jonathan Mattingly that says if you have a drift and minorization condition, then you necessarily have this contractivity condition in one of these strange metrics. Okay. Okay, a couple of other ones. So often it's interesting to take a function of your base metric. So a concave increasing function is the standard choice. And this allows you to handle diffusions where you're sort of contracting in the tails, but maybe behaving a bit strangely in the bulk of the distribution. And so this has sort of been pioneered in the last 10 years or so, particularly by Andreas Eberle and co-authors. But the ideas are much older in some sense. So Mu-Fa Chen and Fengyu Wang sort of pioneered this in the early 90s, but it's really written more in a PDE way than a Markov process way. And it's related to reflection couplings. And for a final slightly weird one, so you can really glue together different metrics in weird ways to ensure that this condition holds. And so another thing that Andreas has done with Matthias Meiker, who was a PhD student of his and is now at Heriot-Watt, is to take a metric that's a combination of a discrete metric with a sort of more standard transport metric. And sort of this is well adapted to things like Mahler, where perhaps in the tails, you expect to have pretty natural contraction in the base metric. And then when you're closer together, you can kind of use the metropolis step to couple things exactly nicely. I mean, that's not very precise, but that's sort of when it's useful. So my contention is essentially that this condition often holds. It often holds with reasonable constants, but it's not always so easy to show. And so that's sort of where I sweep things under the rug today, is I'm going to make this assumption, and it's plausible that it holds, but it's not always so easy to check. So it's sort of bounded honesty in that respect. Yeah, so the sort of hand-wavy thing to say would be the assumption is strong but plausible and occasionally hard to check. But crucially, it has very powerful implications. And under this assumption, you can prove many, many things. It's particularly nice for non-stationary and out of equilibrium processes, and it's very robust. Like you don't, for example, we've been working a lot in the past couple of years about the L2 theory of Markov chains, where your analysis is typically not very robust to your initialization. And if you start with a much colder start, things are quite bad. Whereas for these things, you tend to pay a much more modest price. And so, as I said, it's kind of almost honest in the sense that the assumption will often hold, but checking that it's true is more challenging. And so my view, which is, I go back and forth on this a bit, but I tend to believe that if you have a Markov chain that is exponentially convergent, then a condition like this probably holds with basically the right constant for some metric, but it could just be a very strange and non-explicit metric. And I should emphasize, this is absolutely not proved, okay? And it would be huge to prove it in some ways. And then another point which is nice is, okay, from the point of view of my analysis, I just need it for some metric D, but maybe for your particular application, you care about a specific metric, right? In some cases, you will care about the discrete metric in particular because you want to estimate the probabilities of sets, say. And in that case, what is sort of most practical is even if you don't have contraction in D0, you may be able to find some distance which majorizes the base distance in which you do have contraction. And that can be a very fruitful strategy to try to sort of identify these majorizing distances. Okay. So I'll quickly just describe some of the implications of this contractivity condition, because it's worth appreciating that it does buy you a lot. And I would sort of encourage people to see whether it's suitable for their own analyses. So if you have this contractivity assumption for a reversible Markov chain, you can immediately read off an estimate on the spectral gap of the process. And it's exactly this kappa, basically. So it means that, again, having worked on L2 theory of Markov chains, at some stages you're just kind of starving to find some process which has a spectral gap that you can write down. And actually, this is one way of getting it quite nicely, if the condition indeed holds. Moreover, so this is almost elementary, I guess, is that under this coupling condition on the contractivity, your Markov chain converges to equilibrium exponentially fast in transport distance. Again, the rate is exactly this kappa, okay? And then on the side of this, you can get various things just about the invariant measure of the chain to do with variance, balance, and concentration inequalities. And as I said, Jan Olivier has sort of done the big work on this maybe 10, 15 years ago. It's very readable, essentially because the assumptions are so clean and powerful that most of the results don't take more than a page to prove. So yeah, I'm a big fan, clearly. Okay, so next up is to talk about the applications of these things to just general MCMC, and then this will feed in nicely to the unbiased estimation side of things. So again, it's Olivier in joint work with Alderic Chenat, who also works on sort of functional inequalities for Markov processes and these sort of things. And so in this paper, they basically say, if you have this assumption on a Markov chain and you're doing MCMC type estimation, what does the bias look like? What does the variance look like? And so this sort of addresses this question I put on the slides right at the start. It's also written in a slightly cheeky way, which is a bit fun. So they sort of say, oh, our standard Markov chain stuff tells you that the bias goes down like this and the variance goes down like this, and you have a CLT, but everything's asymptotic. And then they have this nice quote at the end that some even say that confidence intervals disappeared the day that MCMC appeared, which perhaps it was more true in 2010, although I'd be wary of that. But at least they're sort of being clear about what they're trying to do with this paper is, do the strong assumptions, but get the real non-asymptotic guarantees out of it. Okay, so what are the main results of this paper? And you'll see why they're relevant. So the first one is that you get an explicit bound on the bias of your empirical means. So this expectation is saying I start the chain at the point X, I do T0 steps of burn-in, and then I collect samples for T steps. So it almost matches with my notation. And again, you see this nice thing that the bias is going down exponentially with the burn-in, linearly with T. This E of X is kind of like how far away from the center of the space is X on average, or how far is it from other points in the invariant measure. And then of course you have this dependence on the Lipschitz constant of F. So if you're, I guess one mild warning about these methods is if you're interested in functions that are not Lipschitz with respect to the metric that you're working in, then you have to work a bit hard. Okay. Right, and separately, you can get these results for the variances of the empirical means. Again, it sort of scales like 1 over T, as you'd expect. It sort of suggests that you need to take T to be at least 1 over kappa to get stable variances, which makes sense because 1 over kappa is more or less the mixing time, right? So you should think of this term here as being kind of a constant. And these suprema, you don't need to worry about too much. Again, they're sort of not very big. Okay, so that's already very nice. That's for standard MCMC. You have the bias, you have the variance, you can do some sort of honest analysis of what's going on. And so I will now try to tie things back in to these unbiased estimators. So I just in my notes, I've started calling it this for the coupled lagged unbiased estimator, but that may go through some morphing before it becomes a real paper. But okay, so this is the estimator again. You collect samples for L steps, you correct samples forward in time. And so here you can easily do the analysis for the bias of this estimator with the burn-in. You see that it goes down, exponentially somehow with the total runtime of the chain. So if any of B, L, or T are big, then this is small. Mu naught here is the initial distribution. I think when I described it at the start, I was starting from a point, but it's not surprising that things will work from diffuse initial distributions. Okay, so in particular, we confirmed that if you send T to infinity, the bias is 0. That's not a surprise, but at least it's all consistent, right? Okay, so now I can talk a bit about actually doing the variance analysis, which is the main thing I wanted to do in this work. Because if we can't do a variance analysis, I can't really assess whether the estimator fulfills the promise, right? And so, okay, just by sort of the natural properties of expectation, of variance, sorry, I can write it this way, pulling the L squared out the front, and using sort of a plus b squared is less than 2a squared plus b squared. I can pull a factor 4 out the front here and decouple these two variances. The reason why this is nice is because I can neglect the dependent structure, basically. And so we'll see that this first term here is essentially what Julien and Olivier control, right? Because that's just a pure MCMC estimator, okay? And then this term here, this correction term, you see that this will be small if the xt and the yt are close to one another, okay? And so you sort of want to construct the algorithm such that this will hold. Okay, and so now I just do some fairly simple bounds. So the first variance term, I bound in this way. This is almost exactly what is in Julien and Olivier. Okay, I've just reproduced that. And so, you'll get that this term scales like 1 over L in the relevant way, which is right. So if we can ensure that this second term is small, then we can say that the variance of the unbiased estimator is not too much more than the variance of the MCMC estimator. I should also say I've been very crude with going from line 1 to line 2. You can definitely tighten this if you know that the second term is much smaller a priori, say, but it's easier for me to give the simple analysis. And so for the second term, we need to start talking about the coupling that we use between the X and the Y chains. And so I'm assuming here that your coupling is as good as the optimal coupling, okay? And there's reasons why that's not likely to be realistic in some settings, or that there are definitely settings where it is true. But what I should say is, if your implemented coupling is only as good as the ideal one up to a constant factor, then you pay that constant factor and things are more or less the same, right? And you should think in practice, these kappas will be quite small anyways. So that sort of governs what approximations you would make.
And Sam, here, does that mean what, for each pair of starting points is close to the maximal coupling? Is that what you mean?
Yeah. So you only need to do it for fixed X and Y, basically.
Ah, okay.
So if I had, yeah, it's no longer an inf over all couplings, but it's basically saying under the coupling, under one step, can I make things shrink by 1 minus kappa tilde, say?
Right. Okay, thanks.
I think, so there may be settings where your implemented coupling will actually not be strictly contractive under the original metric, which would be annoying, but I can see how it could happen. But somehow you could change the metric again and you would typically be fine. So I think it should be relatively robust.
Okay.
Okay, so for this second term down here, using mostly a bit of algebra and then some conditioning, you can show that the variance goes down like this, right? And so one thing you'll note, so it doesn't depend on L, and it doesn't depend on capital T, okay? So for those things fixed, it's a constant. And then as I send capital B to infinity, this decays exponentially. And so typically, what you should expect is that this second term here, for a well-chosen B, is easy to make quite small, okay? Remember that this first term is really going down like polynomially in L, so. And so from my point of view, I'd say it means that it's feasible to tune this algorithm with reasonable runtime so that the variance is not inflated very much over the standard MCMC variance. Okay, so for me, that means that actually the algorithm is viable, which people know to whatever extent, but actually to validate it. Okay, so to sort of speak at some level about recommendations that stream out of this analysis. So the first thing you must do is run your sort of MCMC steps, the L, the bit where you're collecting samples, you need that to be long enough that running actual MCMC would be okay in terms of the variance, say, because it's the same as IID sampling. You need to have enough samples that the variance is small, and so that's fine. Then once you've picked your L such that you're happy with that, you should tune your burn-in time B such that this excess variance, this second term, which corresponds to the correction terms at positive time, such that that is negligible or small enough. A very easy thing to do would be to just make it at most the same as the original variance, but you can definitely drive it much lower without too much work. And then finally, for tuning T, you can either do it sort of by hand and do it until the bias is negligible. That gives you an algorithm with deterministic runtime. Or you can do what Pierre and co-authors do and wait until you have coalescence, and then you can effectively take T to be infinite and the bias vanishes completely. So both of these are feasible. Depending on your exact hardware setup, the tuning T might be preferable if you want things synchronized, but that's not a strict requirement. And so as I sort of said briefly on the previous slide, by looking at the bounds you get for this analysis, it seems like this methodology is feasible and can actually deliver on the promise that I described. Now, I don't know if it's written in the papers that that's what they hope to achieve, but I think it's sort of a reasonable description of what might be feasible. And so it's nice. There's some validation. I think I have one more thing on recommendations. So one thing which this set of techniques is not perfect for is it doesn't really tell you that initializing at the invariant distribution, say, it doesn't necessarily tell you that that would be good. This is the sort of flip side of the robustness, right? It says you can initialize at a point and everything is fine, but actually initializing at a random point complicates things in some ways. But anyways, it says that it's fine to initialize at a point. And from the analysis, what it basically says is the point you may as well initialize at least if you believe the bounds, is the barycenter of the distribution. So the one where if you take a sample from pi, the expected distance from that sample to the point is minimal, like a median more or less. Again, it's like clear from the assumption somehow, but the bound I get on the efficiency of the algorithm depends primarily on how contractive the coupling is. And so that means that when you're choosing between couplings that you could implement, you choose the ones that are most contracted, right? It's kind of, again, it sounds trivial to whatever extent, but yeah. And I guess you should be thinking about what metrics are appropriate as well. So I think one thing that's difficult in practice is people are often thinking about total variation type contractivity, say, because they want the chains to meet exactly. But as I've said earlier, if you have contractivity and total variation, you have a uniformly ergodic chain. And chances are that's not what the case is, right? And so it sort of encourages you to think, what is a related metric where actually I could have contractivity? And then that means I can compare different maximal couplings, for example, which I think, there's many things these days on how to sample from maximal couplings, but the analysis is typically not great at comparing them somehow. And so I think this is sort of a step towards how you might compare different maximal couplings. Okay. So some challenges, so things that I haven't been able to do, and some of them are not really necessary, but I think challenging and maybe interesting to resolve. So one thing, say I run my chain, can I estimate kappa? So say I know I'm contractive in some metric, but I don't know what my contractivity constant is. Is there actually a sort of methodologically feasible way of estimating kappa? In principle, this would be useful for things like setting confidence intervals and so on. Similarly, finding the best metric in which to measure things can be hard as well. Okay, and even choosing amongst a finite set of them is sort of difficult for the same reason as before. These, I think they don't really affect the algorithm per se, but I think understanding these things would be useful for designing and tuning algorithms. So, another thing which I've been curious about, so if you do this estimator and you do it multiple times in parallel, you can get a variance estimator very easily because they're IID samples from some somewhat complicated process, right? But actually this process that we're generating is a Markov chain, And so I'm curious about whether you can do sort of internal variance estimation. So use the fact that you know you've constructed a Markov chain to get a more efficient estimator of that. Typically, that tends to reduce the variance of the variance estimator and so on, which is appealing. Another standard thing, if you're going to implement an algorithm and tell people to implement it, you need to tell them how to adapt it without getting their hands too dirty. And so coming up with practical adaptation rules for these ideas would be useful. In what I wrote before, there's some indication of what is important to tune out of B, L, and T. Somehow you should take the L big enough that you'd be happy with the MCMC, the B a bit smaller so that the burn-in is controlled well, and then you can either send T to infinity or take it reasonably small in many cases. But at least we kind of know how each of them should scale with kappa, for example. So we know which ones are the dominant terms and which ones are the subdominant terms. Right, yeah, there are some other sort of variants on this this coupling methodology where you have multiple chains. So the way I did it before, right, was you give birth to the first chain and then another one arrives and they couple. But you can kind of have a cascade of these things where, and then another one gets born and blah, blah, blah. And seeing whether you can do a comparable analysis there, which says that there are or aren't benefits to this approach, would be nice. For people who've spent any time thinking about multi-level Monte Carlo, they'll know that the unbiased estimation literature is actually very similar in many ways, and it's all based around good couplings and careful variance control and so on. My suspicion is that this methodology is actually also very well suited to MLMC for Markov chain-based stuff. And so one example of something you could feasibly do here would be do integral estimation with unadjusted Langevin chains, either way, whether they're overdamped or underdamped, because in those cases, you typically know that the chain you're implementing on a log concave target is actually contractive, and you can write down the constant if you know the strong convexity, etc. And so there, you could actually do a completely honest analysis saying like the complexity of computing an integral using multi-level Langevin or something like this, scales like this with the dimension, this with the error, etc., etc. And then a mathematical challenge, which I sort of alluded to earlier, is suppose I have a good chain in the sense that I have exponential convergence in some relevant metric, over probability measures, I should say. So I have, total variation, convergence, L2, etc. Does that mean that there exists a metric D in which I have good contraction? Okay, so that would sort of say if a chain is good, then it must be contractive in some metric. This is not known, but I think if you could prove this, it would make the whole thing much more legitimate, because we know many ways of proving that chains are good, even if it's not through this approach. Okay, and then some miscellaneous stuff. So I'm basically, like at the moment, I more or less have the bias result, which is not new and kind of not interesting because you would do things to be unbiased. I have the variance result, which is putting together a result that's in Julian-Olivier and then doing a little bit of algebra to handle the correction term. And so I'm curious about what else is even worth proving. Okay, and so here's what I thought about, which seemed like dead ends. So I could prove a central limit theorem as the number of replications goes to infinity over processes, say, but that's not interesting, I would say, because it's just IID sampling with a sort of fancy sample. I could send B to infinity, so put a lot of effort on the burn-in, but that's wasteful. I think there's no particular reason to do that. I could send L to infinity, so collect samples over a longer and longer window, but we already have that, and that's called MCMC. And it could send T to infinity, but that's what Pierre does if you have the coalescence. So it's kind of, maybe it's just as it is. Another thing I could do, so in Julian-Olivier, I didn't say this, but they have concentration inequalities for the empirical averages. I could do that, but I don't know if it's practically helpful in the sense that you will do you will put error bars on your estimator using this first line, using the CLT, basically. So, and indeed, you can do the first one without explicitly knowing kappa, whereas for these concentration inequalities, you actually need to have sort of slightly stronger information. So I don't know. I mean, yeah, I suspect there are other things one can ask here, and I think the tools will probably be able to answer them. But each of these directions seem to somehow be deficient in terms of wanting them to be interesting. Okay, and then I think my closing slides. So just to recap on what I've said, So your standard MCMC estimator of an integral will have some bias. And using these coupling methods, it's possible to remove or at least attenuate this bias at a pretty bearable cost. It's not faster, but it's not horribly less fast. Okay. And in particular, when you have parallelization and resources like this available to you, then it becomes interesting because you can actually, in real time, improve how long it takes you to get an epsilon error. So, yeah, and so I think that using these contractivity assumptions is a very natural fit for this setting. As I said, you have the sort of non-stationarity going on, and it sort of suits it very well. It lets me provide variance bounds, which from my point of view, validate the methodology to some extent at the theoretical level. And just as a final thing, like I found this assumption of contractivity is very useful to work with, and many things I'd like to prove just come quite naturally. And I think for non-equilibrium Monte Carlo stuff in general, it's worth thinking about. And so I'm a bit curious about what it could mean for things like adaptive MCMC, for example, and even things like convergence diagnostics, right? And how you might frame those in terms of contractivity. Okay, and then I think I will wrap up there.